Welcome to the video on Chi-square test. Chi-square tests are used for testing entire distributions of one or more categorical variables. These distributions are often stated as counts for multiple categories, usually displayed in a table. That will make more sense when we look at examples. There's going to be three kinds of chi-square tests we're going to look at. First is a chi-square goodness of fit test. We use the goodness of fit test when we have one population and one variable. So we've taken one sample and we've asked every person in that sample one question. The main point of a chi-square test is to ask the question, is the hypothesized distribution correct? So we have some expectation of what we think should happen for this population according to this variable. Is that expectation correct? Is our hypothesis correct? Or in other words, do we have convincing evidence that it is incorrect, that's not correct? Then there's a chi-square test of homogeneity. The prefix homo means same, so a test of homogeneity has to do with the sameness or lack thereof of two populations according to one variable. So is the distribution of one variable the same for two different populations? So I've got two samples, one for each population, but I've asked both samples the same question. Is the distribution of the responses to that question the same for each of those populations? Or do we have convincing evidence that it is different from what we would expect, that they are not the same, different from each other? And then third, a chi-square test of independence, which is also called a chi-square test of association. That has when we have one population but two variables. So I've taken one sample, but I've asked them two questions. And I want to know, are their responses to those two questions related to each other or not? So are their responses according to those two variables independent of each other or not? Do we have convincing evidence that they are not independent? Or in other words, do we have convincing evidence that they are associated, that one is related to the other? Here's the logic of chi-square test. When we observe a set of values from a sample or from an experiment, which is the two ways that we have to gather data, we often want to compare those observed values to what we expected would occur. The size of that difference between the expected value and the observed values, so between what we thought would happen and what actually happened in the sample of the experiment, the size of that gap is a useful thing to know. The bigger that difference, the bigger that gap between them, the less likely it is to get that difference by random chance alone. Or in other words, the bigger the difference between them, the more likely it is that our expectations do not actually match reality, that our expectation was wrong. So instead of a z-score or a t-score, we obtain what's called a chi-square statistic for the distribution. A chi-square statistic measures how far the observed counts are from the expected counts. This is the Greek letter chi, so this is chi-squared. And this is the formula for the chi-squared statistic. For all three of those tests, it's the same formula. The sum, that's what this capital sigma indicates, the sum of the observed value minus the expected value squared divided by the expected value. So observed minus expected gives us the difference between the observed value and the expected value. We're squaring them just so that they all become positive numbers and they don't end up canceling each other out because some of them are positive and some of them are negative. So the squaring just makes them all positive. It's a convenient way that mathematicians use to make numbers positive rather than taking the absolute value, because the absolute value is a cumbersome thing to work with computationally. And then we divide them by the expected because that essentially gives us a relative difference, which is better for the sake of comparison. So we are going to take every single observed value, subtract its expected value from it, square that difference, divide it by its expected value. It's going to give us multiple terms, a term for each of those observed values. We're going to add those all together. We're going to sum those up. That is the chi-squared statistic. Again, it'll make more sense when we do it. The chi-squared statistic is a value on the chi-squared distribution. Now, just like there are different t-curves for different degrees of freedom. There are different chi-squared distributions for different degrees of freedom. Here's a graph showing the chi-square distribution with 1 degree of freedom, which is this sort of exponential decay graph. There's a orange or red one for a degree of freedom of 4, and then there's a green one for a degree of freedom of 8. Those are just 3 examples. Things I want you to notice. The terms on the x-axis, and therefore all the values on the x-axis for a chi-square distribution are always positive. Why? Because the chi-squared statistics are always positive, because we squared those terms, those numerators. So they're always going to be positive numbers. So there's no sense in extending our graph over in the negative direction. There's not going to be any points over there. It is always skewed to the right. The higher the degrees of freedom, the less skewed the distribution is. The reason is because the higher the degrees of freedom, the more terms there are in that chi-squared statistic, so the more things we're adding together to get that chi-squared statistic, and therefore the larger the statistic is likely to be, because we're adding more and more things. The mean of a particular chi-square distribution is equal to its degrees of freedom. So if there's a degree of freedom of 4, the mean, the average value, is 4. If the degrees of freedom is greater than 2, the mode, which is the peak of the graph, is at the number of the degrees of freedom minus 2. So with the degrees of freedom of 4, notice the peak is at 2. With a degree of freedom of 8, notice the peak is at 6. The degrees of freedom minus 2. With the chi-square test, we find the probability of having a chi-square statistic as large or larger than the one that we obtained with our sample or our experiment. So that is an area under the curve, say for example here. It's always going to go to the right. Chi-square tests are always only one-sided. We could have had two-sided tests for a z-test or a t-test. For a chi-square test, it's always one-sided, and it's always headed to the right. So it's finding that probability. Probability of being at the value we were at or larger by random chance alone if the null hypothesis is true. If that probability is small, then we have convincing evidence that the null hypothesis was not true. Just the same logic as we had on previous hypothesis tests. For all 3 chi-squared tests, these 3 conditions must be met. Number 1, it has to be a random sample or a randomized experiment. The second condition is that all the expected counts have to be at least 5. So what we expect in each category has to be at least 5. We'll see how that plays out and how to find those expected counts when we look at our examples. And the third condition is one we're used to, independence. When we're sampling from a finite sample without replacement, we have to check the 10% condition. If we have more than one sample, we have to check the 10% condition for each sample, and we have to verify that those 2 samples should be independent of each other. So those are our 3 conditions. Now let's look at each of those 3 tests individually. We'll do one example for each one. First, the chi-square goodness of fit test. One population, one variable. So we've taken one sample and have one item from each individual in that sample. Is the hypothesized distribution correct? Do we have convincing evidence that it is incorrect? So we have some idea of what should happen. How does what we got in our sample or our experiment compare with what should happen? How well does it fit? What is the goodness of the fit of our observed distribution to the expected distribution? The degrees of freedom for a goodness of fit test is the number of categories minus 1. The number of categories minus 1. Notice for the chi-square test, the sample size does not determine the degrees of freedom. The sample size has nothing to do with the degrees of freedom for chi-square tests, whereas it did for t-test. Now the degrees of freedom is the number of categories minus 1. The null hypothesis for a goodness of fit test will always be that the expected distribution is correct. So obviously you're not going to write those exact words. You're going to write the words that would fit in the context of the problem that you're working on. But your null hypothesis is always that what you expect is correct. The alternative is that what you expect is not correct. So our example. Are the births of children evenly distributed across the days of the week? So are the same number, or roughly the same number of children born on any given day of the week? Or is there a day of the week when they are more likely to be born? Suppose a random sample of 140 births from the local records of a large city yields these results: Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and the number of births in that large city on those particular days of the week. This random sample of 140 births. Do these data give significant evidence that local births are not equally likely on all days of the week? So our null hypothesis is that what we expect to happen is actually correct. What we are expecting to happen is that they are evenly distributed. So the null hypothesis is that the birthdays in this local area are evenly distributed along all 7 days of the week. So we could write that out in words. Births are evenly distributed across all 7 days of the week. Or we could do that with symbols, where we could say P sub sun is the proportion born on Sunday, and our null hypothesis is that that is equal to the proportion born on Monday, which is equal to the proportion born on Tuesday, which is equal to the proportion born on Wednesday, which is equal to the proportion born on Thursday, which is equal to the proportion born on Friday, which is equal to the proportion born on Saturday. It's a lot to write. You could just write in words, the births are evenly distributed across the days of the week. So one or the other of those is all that's needed. The alternative hypothesis is that they are not evenly distributed across all 7 days of the week. So births are not evenly distributed across all 7 days of the week. With symbols, that would be that at least one, so this is the alternative way to write it, at least one of the proportions is not 1/7. Because if they're all the same, we would expect all of those proportions, so we should write that in our null hypothesis, we would expect them all to be 1/7. Because there's 7 days in the week. If they're evenly distributed, every day gets 1/7 of the births. So again, we can write it on words, or we can use those symbols. So notice, with the chi-squared distribution, we're able to test multiple proportions, not just one or two proportions, which we would have done with a z test. I'm going to change my pen here to a smaller ink. Okay. So we intend to run a chi-squared goodness of fit test with an alpha value, let's say, of 0.05. Before we proceed with such a test, we should, of course, check the conditions. Well, we had a random sample of 140 births. So we have a random sample. Check. Let's check the independence condition. There are at least 1,400 births in this large city. So we satisfy that 10% condition. So that means we have independence. And now, the condition that's unique to a chi-squared test, which is that all the expected counts are at least 5. So what do I mean by expected counts? Well, that goes to the null hypothesis. In the null hypothesis, we said they're evenly distributed, which means every day is 1/7 of the total. So what we would expect, and we'll write this out over here, we always, for any chi-square test, always need to write down the expected counts. So the expected counts would be the total which was 140 times 1/7. That's how much we would expect to be in each category if they're going to be evenly distributed. So that is exactly 20. So our expected counts would be 20 births for each day of the week. In this case, the expected count for each day of the week is the same. It will not always be that way. For this test it is that we want it to be evenly distributed, so they would be the same for each category. So when we check our conditions, we would say all expected counts are at least 5. And that's all I need to write there because I've already written over here what the expected counts are, and they're 20 for each day. In other words, what that means is, in my table I have the actual number of births out of that 140 from each day of the week. What I expect to occur is for it to be 20 on each day of the week. On Wednesday it was exactly 20. But these numbers range from 13 at the lowest to 27 at the highest. So it's not always 20. Is that difference between what I expect, which is 20 for every day, and what I actually got, which is not always 20, is that difference enough to say that these births are not evenly distributed throughout the week? And that maybe there's a day like Thursday when they're more likely to be born, or a day like Sunday when they're less likely to be born. So do we have enough evidence to say that? That's what the test is about. So we then calculate the test statistic, which is the chi-squared statistic. There is, of course, a way to do this on the calculator, which I'll show you in a minute. But even if we do it on the calculator, we are required to show some work, to show that we actually know how to calculate this chi-squared statistic. So what we need to do is show at least one term of the sum. Now this is the observed value minus the expected value squared divided by the expected value. So the first one, the one for Sunday, would be Sunday's observed value, which was 13, minus its expected value, which is 20, square that difference, and divide by the expected value, which is 20. Then we would do the same thing for Monday, which would be 23 minus 20 squared over 20. We would do the same thing for Tuesday and Wednesday and Thursday and Friday and Saturday. I don't want to write all that out, so I'm going to put dot, dot, dot. And then put the last one. Saturday was 15, is what we observed, so 15 minus 20 squared over 20. I'm actually going to have my calculator calculate what this is. If I only had 2 or 3 terms, I could do it easily by hand. But I do need to show work like this. Write down at least the first and the last term of my sum. Okay, now I actually have my calculator calculate this, so I go to my calculator. And on the calculator, I plug in my data into a list. So I have that already plugged into L1. I'm going to then go to Stat, Test. I'm going to go all the way down. On mine it's the letter D. You'll notice 2 that are called chi-squared. There's the chi-squared test and the chi-squared GOF test. So what we're doing here is the goodness of fit test, the GOF test. So we're going to choose that one. And it asks me for 2 things, the observed list and the expected list. Well, I've got the observed ones in L1. I need to tell it what I expect, and I need to put those in L2. So I'll go back to L2, Stat, Edit. In L2, I'm going to put what I expect. And what I expect is 20 for each day of the week. Again, for this test, since we wanted them to be evenly distributed, those expected counts are the same for every day. We will have goodness of fit tests where those expected counts are not the same for every day, for every item. Now that I have those, we can go back and do the stat test and the chi-squared goodness of fit test. The observed are in L1, the expected are in L2. I need to tell the degrees of freedom. The degrees of freedom is the number of categories minus 1. Categories here are the days of the week. There are 7 of them. Minus 1 is 6. So I have 6 degrees of freedom. And I will calculate. Enter. It calculates the chi-squared value to be 7.6 and the p-value to be 0.26889667777, the degrees of freedom of 6. This CNTRB is a list of all of the terms of that sequence that was added together. I don't need to write those down, but if I actually wanted to check what those were, it calculates them and stores them in a list called CNTRB, which I could access later if I wanted to. So chi-squared is 7.6, p is 0.269. Chi-squared is 7.6, and the p-value, which is the probability that the chi-squared statistic is greater than or equal to 7.6, is 0.269. So just like before, we have the test statistic and the p-value. Here our test statistic is the chi-squared value. And I need to write down that this is with a degrees of freedom of 6. Okay. So I will make my conclusion. The conclusion will work the same way it has worked for all of the other hypothesis tests that we have run. My p-value of 0.269 is greater than my alpha value of 0.05, so I fail to reject H naught. When I fail to reject, that means we do not have convincing evidence that the births are not evenly distributed throughout the week. Now, it may sound like it's a double negative, that we do not have convincing evidence that the births are not evenly distributed throughout the week. But those negatives are not canceling out and saying that we do have convincing evidence that the births are evenly distributed. That would be accepting the null hypothesis, which we do not do. So these are not canceling out. We do not have convincing evidence to say that the births are not evenly distributed throughout the week. So that's a goodness of fit test. How about a chi-squared test of homogeneity? A test of homogeneity is when we have two populations but one variable. So we have two samples, and we have asked them one question, and it's the same question for both of them. And what we're ultimately getting at is the distribution of that one variable the same for the two populations? Do they agree in their distributions according to this one variable? Or do we have convincing evidence that the distribution is different for each of the two populations? Here our degrees of freedom is the number of rows minus 1 times the number of columns minus 1. So this appears in a table, a two-way table. We take the number of rows minus 1, multiply by the number of columns minus 1. That is the degrees of freedom. The null hypothesis for a test of homogeneity is that there is no difference in the distribution of a categorical variable for several populations or treatments. So that the distribution is the same for both populations. The alternative hypothesis is that there is a difference. So we're trying to find evidence to say that they are not the same, that they do not agree. Here's our example. Two American and UK students, or students here are children from ages 9 to 17, have the same preference of superpower. This is actually following up from an example we did in a warm-up way back in the first unit of the course, where we looked at the distribution of U.S. children by superpower preference, and we analyzed that, I think, for boys and girls, and we looked to make a comparative bar chart between boys and girls. So we have the same U.S. statistics, but now we have the U.K. statistics, and we want to know, are they the same? A random sample of 200 children in the UK and a random sample of 215 children in the US yielded these results. So the superpowers are fly, freeze time, invisibility, super strength, or telepathy. Do these data provide convincing evidence that the distribution of superpower preference differs among US and UK children? Do they prefer to have a different superpower if they could? So our null hypothesis is that there's no difference between the UK and the U.S. children in superpower preference. And I'm going to write it out like that. The null hypothesis is U.S. and U.K. children do not differ in superpower preference. The alternative hypothesis is the opposite of the null hypothesis, which is U.S. and U.K. children do differ in superpower preference. Do I have enough evidence to say that that is the case? So if we look at the table, those numbers are not the same in each row for the UK and the US. Are they far enough apart to say that they are actually in reality different? Certainly they're different for these two samples. But are they different for the entire populations. So we are going to run a chi-squared test of homogeneity. We check the conditions. We have 2 random samples. Check. We can say that UK and US children are independent of each other, or our samples, let's say, of UK and US children are independent of each other, and 200 times 10 is less than the population of UK children, and 215 times 10 is less than the population of US children. So we satisfy independence in the 10% condition. And then we need to verify that the expected counts are all at least 5. In order to do that, we need to calculate the expected counts. How do we do that? For a two-way table. So let's think this through. We're going to have an expected count for each of the interior cells of our table. So not for the total columns, but for each of these 10 cells on the inside. For this box, the UK children who would prefer to fly if they could. Here's the way we'll calculate that value. We'll take the fraction of children overall who would prefer to fly. That's 99 out of 415. So the total for the row divided by the total for the table. That's the fraction of all children who would prefer to fly. We're going to multiply that by the number of people in the UK sample, which is 200. And that should tell us how many should be from the UK and prefer to fly. So 99 divided by 415 times 200, which is 47.7. So UK versus US for flying, we'll have 47.7. If you do that for each one, for the US we'll do 99 divided by 415 times 215, and that'll give us 51.3. For freezing time, we'll do 96 divided by 415 times 200 for the UK and get 46.3. For the US, we'll do 96 divided by 415 times 215 and get 49.7. That's how many US children we would expect to choose freezing time. And so on and so forth. And we create a table of all of the expected counts. Writing them in a table is a perfectly nice and neat and organized way to write them. No need to total them up because they're going to have the same totals as they had in the original table. So notice each of those 10 numbers definitely bigger than 5. So we check and meet our condition. All expected counts are at least 5. Where we've written the expected counts in this table up here. So expected counts, again, means what we would expect to happen if the null hypothesis is true. So if the null hypothesis is true, we would expect the proportion of UK children who chose to fly to be the same as the proportion of US children who chose to fly. Since those sample sizes are different, that doesn't mean that we end up with the same number in each column of our table. That means the proportions are the same relative to the size of the samples. So that's how we end up with these numbers. And if the proportions are going to be the same, since there's more people in the US sample, those numbers will end up slightly higher than the numbers for the UK sample, which are fewer people in it. But the proportions are the same for each row in the expected counts. But notice those are not the same numbers we got in the samples. So is the difference between those enough to say that they are in fact not the same? That's the point of the test. So we're going to do this with an alpha of 0.05. We're going to have a degrees of freedom of the number of rows minus 1 times the number of columns minus 1. Well, how many rows do we have? We have 5 rows. So we'll have 5 minus 1 times the number of columns minus 1, which is 2 minus 1. So 5 minus 1 times 2 minus 1 is 4 times 1, which, last I checked, is 4. So the degrees of freedom is 4. Our chi-squared statistic, we need to at least show one term of our sum. So let's take the UK flying, which is 54 as the observed value, but 47.7 is the expected value. So observed, 54, minus the expected, 47.7, squared, divided by the expected, 47.7, plus dot, dot, dot. So we need to indicate that we know how to actually calculate this, though we're going to calculate it on the calculator. So we'll go and we'll put our data into the calculator. The difference here is we have an entire table to put into the calculator. I can't do that in a list form. But instead, I will do it as a matrix. So I will choose second and matrix, which is right below the math button, the x to the negative 1 button. I will choose second matrix. And it has listed there a whole bunch of matrices, which it identifies by capital letters. I will move over and choose edit. I'm going to edit the first one. I've already put in my data for the sake of time in this video. But I would have to tell it that it's 5 rows and 2 columns, so a 5 by 2 matrix, and then I enter the data. Okay, once I have it in there, I can go to Stat, Test, and I'll choose the chi-squared test, specifically not the chi-squared goodness of fit test, the chi-squared test, which is letter capital C on mine. Don't necessarily assume it's the same on yours. Enter. The observed values I put into matrix A. Now, where it says expected, I do not have to put in the expected values. It can calculate them for me. And what it's doing is asking me where I want it to put them. I want it to put them in matrix B. So it will do that for me, and I will calculate. It gives me the chi-squared statistic of 6.29 and a p-value of 0.178 with the degrees of freedom of 4, which we already knew. So 6.29, 1784. 6.29 is my chi-squared statistic. The p-value, which is the probability that x squared is greater than or equal to 6, not x squared, chi-squared is greater than or equal to 6.29, is 0.1784, which of course is greater than 0.05, so I fail to reject each not. We do not have convincing evidence for the alternative hypothesis, which was that the distributions of superpower preference are different for UK and US children. Now, just to show you, it has put those expected counts into matrix B, so I can go to second matrix, and I can just look at matrix B. I don't have to edit it. I can look at it, click enter, and it will show me exactly those expected counts that I calculated already. So if I don't want to calculate those by hand, I can actually run the chi-squared test, then write down the expected counts that it stores in matrix B for me, sort of retroactively verifying that they are in fact all greater than 5. And if they weren't, then that chi-squared test that I already ran shouldn't have run. Alright, one last test, the chi-squared test of independence. Now, a test of independence is when we have one population but 2 variables. So one sample that we've asked 2 questions of. And what we want to know is, are those 2 variables, their responses to those 2 questions, independent of each other? Or do we have convincing evidence that they are, in fact, associated with each other? The degrees of freedom here is the same as it was for a test of homogeneity, the number of rows minus 1 times the number of columns minus 1. The null hypothesis is that there is no association. Or, the same thing as saying there is independence between these 2 variables. And the alternative hypothesis is that there is an association, or to say that they are not independent of each other. For example, in the United States, there's a strong relationship between education and smoking. Well-educated people are less likely to smoke. Does a similar relationship hold in France? Researchers recorded the level of education and smoking status of a random sample of 459 French men aged 20 to 60 years. Here are the results. Their education level, primary school, secondary school, or university, and their smoking status. Non-smoker, former smoker, moderate smoker, heavy smoker. Is the relationship between smoking status and education level in France statistically significant? So, are education and smoking status independent, or are they associated? Our null hypothesis for a test of independence is always that, yes, they are independent. So, education and smoking status of men, because our sample is all men, we can't generalize it to the entire population of men and women. The education and smoking status of men in France are independent. We're trying to see if we have evidence to say that they are not, to say that there is some kind of relationship between them. So the alternative hypothesis is that education and smoking status of men in France are not independent. Or we could say are associated. So we will run chi-squared test of independence, also called the chi-squared test of association. You can call it either one. Doesn't matter. We'll do so with an alpha of 0.05, assuming that, of course, we satisfy the conditions, which we do if all expected counts are at least 5. So I'll have my calculator calculate those expected counts, because I don't want to do it, and I'll just make sure that they were all at least 5. If not, I'll get out my eraser and erase. So we will run a chi-squared test of independence with alpha equal to 0.05. Doing so requires that we calculate the chi-squared statistic, which again my calculator is going to do for me. I need to write at least one term for it. I don't have the expected counts yet, so I will actually write down that one term after I find the expected counts. The observed value for that first term, though, is 56 minus whatever its expected is squared divided by the expected. And we will get that in a moment. And we'll find the total. So we'll go to the calculator. Don't need that matrix B anymore. What I've done, though, already is stored, this time in matrix C, my data from that table. I just plugged it into a 3x4 matrix. So I'll go to stat, test, I'll choose the chi-squared test, which I know already is letter C. Now I put my observed values into matrix C, so I need to change that and go to second matrix and choose letter C, number 3. And I can still have it put the expected ones in matrix B because I don't need the old expected ones anymore, the ones from the previous test. I'll run the calculate, and there it is. Chi-squared statistic is 13.3. The p-value is 0.0384. So 13.3 is the total for this. The p-value, which is the probability that chi-squared is greater than or equal to 13.3, was 0.0384 with the degrees of freedom 6, because there were 3 rows, which minus 1 is 2, and there were 4 columns, which is 4 minus 1 is 3. 3 times 2 is 6. Number of rows minus 1 times the number of columns minus 1. Okay, now I need to write down what those expected counts were. So I need to go snag them from matrix B. So I'll go second matrix, and I'm just going to take a look at matrix B, click enter, and there they all are. I need to write those down. So 59.5, and there they are. Notice, all greater than 5. So I meet that condition that I already said that we met. Now I need to take the first one, the 59.5, which corresponded to an observed value of 56, and I need to plug that into the chi-squared statistic in that first term of that, so that I'm showing enough work. I do need to write down all of those expected counts. So my p was 0.0384. Well, 0.0384 is less than 0.05. So we reject H naught, which means we have convincing evidence for the alternative hypothesis that the education level and smoking status of men in France are associated to each other or are not independent of each other. Sound good?